And with that, we go to our final speaker for the day. Stephen Wolfram truly needs no introduction. He's the creator of Mathematica, Wolfram Alpha, and the Wolfram language. Besides being in all of these advanced fields, he is the author of A New Kind of Science, the originator of the Wolfram Physics projects, and of course, the founder and CEO of Wolfram Research. And over the course of more than four decades, he has been a pioneer in the development and application of computational thinking. He has logged his life and everything that he's doing very, very extensively. So I'm sure it's going to be a lot of interesting sharing that he has on that subject. And he's been responsible for many discoveries, inventions, and innovations in science, technology, and business. So I'm sure this is going to be like a true highlight with a breadth of information that we all can learn from. So I'm truly honored that we managed to have him join us virtually this year. And before I hand over to him to share his learnings, I want to also make sure there is a special price. So there's a type form that you can fill out. We'll post the link into the main sessions in a second. And you can have a chance to win several 10-minute one-on-one sessions with Stephen Wolfram. So pay attention to this link, fill this out, and please all join me in giving a warm welcome to Stephen Wolfram.
Great. Hi there. Well, thanks for inviting me, and nice to see you all today, this morning, afternoon, whatever it is for you all. So I want to talk a little bit about the idea of computation, kind of my emerging view of computation and the things that it can bring to the world. And I've been involved over the last, 40 years or so in trying to actually create things that sort of realize the promise of computation. The biggest of those is this thing I call Wolfram language. And let me maybe start by showing you some very practical things about what that's about. So kind of the idea is how to represent the world computationally. How do we take the things that we're used to dealing with in the world and make them so that we're able to have a computer deal with them? And in a sense, what we're trying to do is something a little bit similar in the sort of long view of history to what was done, 400 years ago or so with mathematics. Before 400 years ago, people, when they were describing things mathematically, would just use words. They would talk about mathematics. Then people invented things like plus signs and equal signs and so on. And suddenly there was this kind of streamlined way to talk about things mathematically. And then algebra got developed, and then calculus and so on. And then that led to kind of the mathematical sciences and a lot of the engineering and technology that we have today that came out of kind of this mathematical tradition. What I've been interested in for a long time is doing the same kind of thing with computation. Computation is kind of a richer raw material than just mathematics. It kind of encompasses all imaginable kind of definite rules for doing things. The question is, how do you represent how do you represent those rules? How do you form kind of a notation for computational ideas? And so the thing that I've been doing for a long time is building our kind of computational language, we call Wolfram language, that is an attempt to represent kind of everything in the world computationally. And kind of the difference, I suppose, in when you think about things like programming languages were intended as a way to take the raw hardware of what a computer does and kind of wrap that in a way so that you could sort of manage the bureaucracy of programming things and telling the computer what to do. What we've been trying to do with our computational language is find a way to kind of represent everything in the world, not just the things that are intrinsic to a computer, and deal with them computationally. So the typical interaction with our language is through notebooks. It's a funny thing because we first introduced what's now Wolfram language in the form of Mathematica almost a third of a century ago. In October, it will be a third of a century since Mathematica was first released. And one of the most trivial aspects, we thought, of what we were doing was this concept of notebooks as a form of interaction. 25 years later, people other than the people who've been using them for a long time in our technology stack started thinking notebooks were cool. I have to say that there are many, many other things that we've done which I think are much deeper and more interesting than notebooks, which I would say have been widely used by people using Wolfram language and Mathematica and so on, but which have not generally been absorbed. And I'm kind of after you've been at something for a third of a century, you kind of begin to think in slightly longer terms. And I'm kind of in the, well, I don't know, it's another 30 years, another 50 years before some of these things are fully absorbed. But one of the things that I suppose is a thing that I kind of have felt and kind of pride myself on doing is building things which are kind of built for the future, so to speak. And really then the question is, can you take those sort of artifacts from the future and use them today? All right, let's start off with something totally trivial. Let's just start interacting with Wolfram language. And let's say we just say, let's make a random graph, 100 nodes, 200 edges. Okay, now the idea, one of the key ideas of Wolfram language is that it's a symbolic language. So if I say X, it's just X. It just represents it doesn't need to be given a value, a thing that the computer intrinsically understands. It can be just dealt with as a symbolic kind of thing. And if you're doing, something mathematical, you could say, X then is something like an algebraic variable here. In this case, the thing we're dealing with is a graph. So I could pick up that graph and I could say, make a community graph plot of that, and there's the result. Or I could say, I don't know, I could pick up an image. Let's see if I can get an image here. Let's pick up an image and just put it in here. And then I could say, take that image and say, I don't know, do edge detection on that image. And then I'll get the result there. Or maybe I can, let's live dangerously and let's see whether I can say, I don't know what will happen here, but let's say if I can say text recognize that, see whether it can pick up anything from that, see whether it manages to find that, it's got to load some machine learning based thing for doing text recognition, which it's just going to load into the local engine that I have here. Let's see whether it recognizes anything there. That's a bit disappointingly slow, but see what happens. You know what? I have a very bad. Okay, I didn't get anything. Oh well. But I could take this and for example, let's say by the time you're dealing with things symbolically, there's kind of all of these. One of the things that's great about a symbolic language is everything is kind of represented in the same way as a symbolic expression. So I could say something like, make a nest list of, X, f of X, f of f of X, and so on. But that nest list could also be applied. I could say blur something, and I could take that image there, and I could say make successive blurrings of that image. So let's say we make 10 successive blurrings of that image. I don't know, we have to pick one of them up here and see it. We'll see that, okay, it got very blurred at that point. So kind of the idea of the language is to be able to take any kind of thing and be able to deal with it to be able to manipulate it. So I don't know, we could take another kind of thing. Let's say we take, let's go ahead and capture some audio. Let's say, let's see, hello, let me talk to my computer. So then I should get back a piece of audio, and I could say, let me make a spectrogram of that audio. So that's the that audio as a function of time, the frequency, and see I can try. I'm not sure this might require loading some elaborate thing in, but let's try. That was on 2 lines ago. So let's see if I can recognize that piece of speech. See whether I can. Again, this might require loading in. Okay, there we go. Not too bad. Missed the first H. Something here wasn't picked up as it might have been, but that's just using machine learning to do that. Maybe I can let's try doing something like this. Let's say I do that, and let's see whether I can pick out nouns in that sentence. Let's see again. Okay, so it managed to find the noun computer in that sentence. So one of the kinds of things here is be able to manipulate lots of different kinds of things, whether it's graphs or sound or images or whatever else. Another kind of thing is to like know about the world. So, for example, at a very simple level, we might say, okay, give me a list of words in English. There's a list of words in English. Let's say I want to take the first letter of each of those words. And now let's make a word cloud of the first letters of each of those words in English. and we should get a result here. Maybe we can say, I don't know what other, let's see. I wonder whether we have Romanian as a language here. Let's see. This is not promising. It does not autocomplete. Well, let's at least try, I don't know, let's try Russian or something here. And then we can do the same thing. Maybe we can just let's try word translation. I wonder whether we can translate hello into, let's see whether we can do this, English. See if we know this. I wonder why that isn't auto-completing. Oh, okay. Well, maybe it would work here. Let's just try. I'm now curious. No, okay, it didn't work. Oh well. Okay. Or we could say, for example, let's say we want to translate. Actually, I'm curious here. If we want to say translate the word hello into all languages that we know, let's see what happens there. And this will hopefully give us some, I'm curious how similar hello is in different languages. So there's hello in lots of languages. And maybe we could try let's first of all transliterate them all into English characters. And then let's say, transliterate that. And then let's take the first character from each of those and see what we get here. And then let's just make a word cloud of the values that we get out from that. Oh, no, actually, we need to do one more thing here. We need to take the first word for hello in each of those cases. So we need to say first of that. All right, let's see what this does. So hopefully this will, oops, what did I do wrong? Did I get that right? Help. Oh, no, very bad. Okay, so hopefully this will give us, oh, well, I did something horribly wrong here. Well, that's what I get for trying to do everything in one go here. So we could say, all right, let me just because I don't want to have it do something horribly wrong, let's get the first element of each of those languages. And then let's say, okay, so this is going to give us the first word for hello in each of those languages. And then let's say we want from each of those, let's go ahead and get what the actual value of hello is. Then let's say take the first letter in the string, and then let's make a word cloud of the results. Let's see, and we actually want one more thing, which is we want to say transliterate those so that we have just in English characters. So perhaps this gives some sense of what. There we go. Hopefully that will work. Okay, there we go. That's kind of interesting. Okay, so H and S seem to be the most popular first letters for the word hello. So anyway, this perhaps gives some sense of the kinds of things that you can expect to do in our computational language, where we've kind of we've tried to get sort of all of the knowledge of the world in computational form and set up in such a way that all these different pieces interact and one can kind of flexibly do things. Now, for example, I could go on and we have lots of other knowledge of the world. So, for example, if we say Romania, that's again a symbolic thing. It represents the country Romania. And so we could say, for example, something like, what's the population of Romania? And we should get some current result. Or we could say, for example, give us the population of Romania over time. And now that's a time series. Now we could say, make a plot of that as a function of time. So that's the population as a function of time for Romania over course of a little while here, going back to apparently to 1600 or so. So we could, for example, ask, I don't know, let's say, let's try taking, let's try seeing what happens if we say something like, let's just take an image of, we could do sort of image processing kinds of things. We can take an image of the Romanian flag and we could say, what are the dominant colors in the Romanian flag? And then we could say, for example, okay, so it should give those three colors. And we could, for example, start asking questions like, let's just take, we could ask, for instance, let's say flags of countries in Europe. So that's using natural language. What will then happen is that natural language will be converted to our precise symbolic language. So that's now saying, that's turning it into something which says the entity Europe and countries and flags and all those kinds of things. And now we'll probably get outrageously high resolution versions of all of these flags. But we could, for example, ask questions like, in the space of images, which flag here? Oh, for example, I might say just make a feature space plot, which is going to sort of lay out these flags in some kind of machine learning feature space. And we could ask questions like, which other flag is the Romanian flag closest to? Those kinds of things. And we could ask things like we could do more geographic kinds of things. So, for example, we could say, let's do this. Let's say, this is taking its time because all of these flags are perfect. They're kind of perfect vector flags, and so it's trying to figure out probably. Oh, there we go. It's trying to carefully show us the kind of, there we go. There's our perfect vector flag, whatever country that is, which I don't actually know what it is. Actually, now I'm curious again. Okay, so there's our layout of flags. Let's actually, just for fun, I'm pretty sure we have a classifier for. Let's use machine learning here. Let's say this is a. Let's see, what is it? Country flag. Let's see whether we can, again, I'm living dangerously because I don't actually know what will happen here, but let's say I feed it that country flag, okay, and it tells us using machine learning, it's a pre-trained classifier that says that's a Spanish flag. By the way, if we wanted to, we could kind of see what it looks like to do machine learning training, but maybe I'll show you. Let me just show you something geographical first, and then let me show that. So, then let's say something like let's see. Well, we're getting some questions that are about very, very different kinds of things. Well, let me finish on sort of a little bit of a kind of a sketch of this sort of computational language idea, and let me start talking a little bit more about kind of the bigger picture of computation and the science around it and so on. I mean, this is kind of the tool set that I've built, that our company has built, that gets used by lots of people doing kind of R&D and education, and now increasingly also lots of kinds of production types of things. And kind of the idea is, let's build sort of computational intelligence into the underlying computational language that we have. It used to be the case when I first started using computers, there was just a raw computer. Then computers started having operating systems, user interfaces, networking, things like that. It's our kind of vision and intention to make it be the case in the future that computers have sort of built-in computational intelligence everywhere. And you started to see that. I mean, our Wolfram Alpha system has been built into Siri from the very beginning. And you'll see now in the latest versions of Excel, you'll see a bunch of our technology built into its ability to know about all sorts of kinds of data and so on. So this is kind of the rise of kind of this concept of computational intelligence and being able to deploy it everywhere. Let's just try asking something like, let's say, I'm just curious, if I say something like GeoNearest, I typed the wrong thing. I say something like GeoNearest capital of Romania. And then I'm going to say, actually, I want to say something like, I want to know volcanoes that are, let's say, I want the 10 volcanoes that are closest to the capital of Romania. And let me now say, make a geolist plot of those things. And okay, that's where they are. And we could, for example, we could say, I don't know, let's pick one of those. Let's pick whatever this is, and let's say something like find the geo elevations around that. Let's say a geodisk. Let's say you guys use kilometers. Let's say 20 kilometers around around that volcano. So this is now going to find the elevation of the Earth 20 kilometers around that. And let's say, let's see what I can try doing this. And let's try now plotting, just making a plot of what that terrain looks like. I'm a bit suspicious about why everything's running so slowly. This is very strange. Anyway, okay, there we go. So this is now that's now the kind of the elevation of things around that volcano. So it's kind of been important to me to see all these different things about the world that now become computable, whether it's things about elevations, whether it's things about, I don't know, we could say something like, I don't know, let's say let's pick a random entity, let's pick movies. Let's say we want 20 random movies. Okay, I could be living dangerously here, but let's try and pick up the movie posters of those 20 random movies. Again, this is all stuff that now becomes computable data, and we can go through and, for example, I don't know, we could say something like chromaticity plot 3D. We could say make a plot of where do those movie posters, oops, I needed to get rid of the ones that were missing here. So let's say, so now we can say sort of where in color space do those movie posters lie? So anyway, the kind of the concept here, as I say, is to take all of the kind of the sort of everything that we sort of like to think about and be able to represent those things in a precise symbolic computational way. And there are lots of different domains that we've been doing this for. And kind of this is the work of the last 40 years or so for me, is kind of creating this kind of whole framework for representing kind of the world computationally and having a way so that we can talk about things computationally. And that's important both in terms of communicating to our computer. It's also important for us. I mentioned mathematical notation at the beginning. When I think about things, try to think about things computationally, and I'm thinking about them using the language that we've created. That is the medium that I end up being able to use to think about things computationally. So the thing that, so maybe I can talk a little bit about what, I mean, there's lots of different kinds of things to show, and I'd be happy to talk about different things if people are interested, whether it's, doing blockchain things, or whether it's doing geometry, or whether it's doing natural language processing, or all kinds of other things that are all kind of, that has been our goal to sort of integrate all of these into this computational language. And kind of my big life activity, I suppose, for a long time has been the design of this language and taking all these different kinds of things that can be made computational and actually understanding how to fit those together in a coherent way in this language. For those who are interested, one of the things I've been doing for the last few years is live streaming our kind of internal design meetings where we're designing all of these features and all of these capabilities that you're seeing. So we just passed our 500th episode of live streaming our internal kind of design process. And it gets pretty interesting because in any given area, there is one needs a sort of deep understanding of that area to be able to successfully kind of whittle it down to be able to make a language design for that area. It's kind of a little bit like doing science, where you say there are all these things in the world. What are the underlying scientific laws that govern those things in the world? In designing a computational language, you're doing the same kind of thing. What are all these sort of surface level computations you want to do? Then what are the kind of underlying primitives that allow you to do those in an effective way? All right, so I showed you a few practical things. We can also talk about how this is all deployed in the cloud. I could probably deploy this notebook here just for fun. I could just, this contains a bit of large stuff. So let's see, if I say publish to cloud, those giant flags will probably, let's go ahead and let's just assign a URL automatically. Let me go ahead and publish this to the cloud. And then there's a cloud version of this, which should eventually show up. And there should be a QR code here that you can, or I can just put it in chat. I think it was a big mistake there to have every one of those flags of Europe together with every detail of the crest of whatever it was in Spain and everywhere else included in this notebook. But anyway, it'll steadily save to the cloud, and we should get a way that you can all go and play with this, and you can actually not only can you see what's there, but you can also actually compute things and do computations in the basic version of our cloud using this notebook. Okay, that will eventually save. Okay, but let me talk now a bit about kind of the more at a more theoretical level about sort of the idea of computation and so on. So the thing that one question is, so what is computation somehow capable of? Oh gosh, we're getting all kinds of questions. What is the most important feature we can find in Wolfram language not available in current languages? Let me explain. Programming languages are programming languages. They are intended to do things that are for computers to do. They manipulate arrays. They compute things with strings. They do things like that. What we're trying to do is to compute things in the world. We're trying to deal with, I don't know, knowing about cities, being able to compute, traveling salesman tours of cities, things like this. That's not what languages do. Programming languages are intended, ordinary programming languages are intended to be wrappers around the specific things the hardware of a computer does. Now, people have built libraries in lots of languages, of big sort of spokes of libraries that do all kinds of particular things. Those libraries do all kinds of interesting things. They are not intended to be particularly coherent. They're built for some particular purpose. What ends up happening in Wolfram language is we're doing all these things in a coherent way. And by the way, the foundation of the language is this idea of symbolic computation. So it means that you can actually pick up a thing that represents a city and manipulate that. That's the kind of thing that's sort of an idea that is kind of, it's in a sense an obvious idea from the history of mathematical logic and so on, but it's not an idea that really has emerged anywhere else. The other thing that is sort of an important piece of the story of Wolfram language is just knowing a lot of stuff about the world. And for the last, several decades, we've been kind of making computable things about the world so that you can actually not only kind of get that output that a human can look at, but you can also do computations with it. So, I mean, this is, but the kind of the bigger story here, let me just, the bigger story is just the goal of being able to represent the world computationally, to be able to say, I have a particular chemical, I have caffeine or something. I want a computational representation of that. I want to be able to take the graph that represents caffeine, and I want to be able to do computations with that graph. I want to be able to have all these things in a form that can be readily manipulated computationally, which is completely different from what traditional programming languages are not about. That they do not have a representation for a caffeine molecule. They have a representation of, this is a set of structs and arrays and this, that, and the other. That is their low-level representation. So that's kind of the idea. So let me say a few things about let's see, what was I going to do here? I was going to copy this for what it's worth and put that in the chat here. Let me say a few things about kind of the bigger picture of kind of computation. I see people are asking questions that are much more kind of big picture questions. So let me try and address some of those big picture things. And let me just save another notebook here. Okay, so one question is this idea of computation. What can it do? So I got interested in sort of a version of that in basic science back 40 years ago or so now, and it really came out of the following issue. If we look around the natural world, we see lots of things that look very complicated, whether it's a snowflake growth or whether it's a pattern of fluid flow or whether it's the structure of a galaxy, all those kinds of things. There's a lot of apparent complexity in the world. And so I got interested in the question of where does all this come from? What's this kind of secret that nature has that allows it to make all that complexity that we don't have when we typically make things in engineering? And so I've been doing physics, particle physics, things like that, and knew all kinds of fancy methods from mathematical physics. And I tried using those to address these questions about sort of where do things like complexity come from, and found out those methods really didn't work at all in doing that. And so I sort of realized one needs a different kind of paradigm for thinking about making models of things in nature. And the thing that I started thinking about was, well, what happens if we generalize beyond mathematical equations and so on? We say, well, let's just use arbitrary kinds of rules to describe the world. Well, what's our raw material for arbitrary kinds of rules? The raw material is we can think about in terms of programs. And so then the question is, if there are programs that are kind of driving what we see in nature, what kinds of programs might they be? They're probably not programs of the kind that we're used to writing, where we specifically build, thousands, millions of lines of code to do some particular thing. They're more kind of programs in the wild. So the question is, what do programs in the wild do? And so we want to start off by looking at very simple programs. So particular kind of program that I looked at a lot are things called cellular automata. And the way these work is there's just a line of cells. Each one is either black or white. And this is a program that says, given a particular cell and its two neighbors, what will the color of that cell be on the next step? So we can run this program. We can say, let's make a picture here. We say, let's take that particular program and let's say, let's run it starting off from one black cell. And let's say like this, and let's say, do that. And we have this program. It's a very simple program, and it produces a very simple result. The question is that always the case? Does every simple program produce a simple result? Let's try another program here. Here's another program. This one here, let's try running that one. Well, this produces a slightly more complicated result. If we run that one a bit longer, we'll see that it produces a nice, elaborate, intricate pattern, a nested fractal pattern. But although it's very intricate, there's still definite regularity to it. It's like we saw there was a simple rule, we got out something that had a lot of regularity to it. So the question is, what if you kind of just do the experiment? You just sort of point your telescope out into this computational universe of possible programs, and you ask, what's out there? What possible programs are out there? And what do they do? So let's take a look at a collection of, let's say the first 64 possible programs of this type. And here's what they do. Each one of these is a different program. Some of them they just make stripes. Some of them just make a single line like this. Some of them make those nested patterns. But then if we scroll down a little bit further, we get to my all-time favorite science discovery, which is Rule 30, one of these very simple rules. And well, that's what it does at the beginning. Let's look at it a little bit longer. So let's say this is Rule 30, and let's run it longer and see what it does. That's what it does. This is, to me, a very remarkable thing because there's a certain amount of regularity over on the left, but many aspects of this pattern kind of look completely random. Yet this pattern comes from this extremely simple rule. We just started off with one black cell, and this is what we get. And for example, if you look at the center column here, I put up this prize actually recently for figuring out pretty much anything about the center column of this particular thing, because for all practical purposes, it seems completely random. In fact, it's been the pseudo-random generator that we used for a long time in Wolfram language was based on Rule 30, and it's also been used as a crypto system and other things like that. It is remarkable that from something so simple, you can get something so complicated. But in a sense, what this is kind of a clue about how nature works. And in a sense, this phenomenon in the computational universe of possible programs, it just turns out that complex behavior is easy to get. And that's kind of the secret that nature is using to make lots of the complexity that it makes, whether it's in fluid flow or snowflake growth or whatever else. And so this is, and there are all sorts of principles that are important in understanding this. So, for example, we can say, let's do science on Rule 30. Okay, great. Science tells us we can make predictions of things. Let's try and predict what Rule 30 will do after 1 million steps. Well, clearly, we can just run Rule 30 and see what it does after 1 million steps. But can we kind of jump ahead and say, what will it do, sort of by coming up with some clever scientific technique, say, what will it do after 1 million steps? Well, it turns out that there's a phenomenon I call computational irreducibility, which says you really can't do that. In a system like this, there's no choice but essentially to follow each of those steps and just see what it does. So in a sense, even though we know the underlying rule, we might have thought, okay, if we know the underlying rule, we're done. The science is finished. We figured out everything. But it isn't true. There's this kind of irreducible amount of computational work that's needed to figure out what will actually happen in the system. And that's kind of an important conceptual idea that affects a lot of things about of thinking about kind of what the limits of what science can tell us are and so on. I should say that one of the features of this is it's related to a thing I call the principle of computational equivalence, which basically says if you think about this thing as a computation, what this is doing as a computation, that computation is as sophisticated as any computation that anything can do. So that means, for example, that if we are trying to say we have our brains, we're doing computations, how do our brains compete with the computations that are going on in Rule 30? What the principle of computational equivalence says is that we will not win that competition. And that's why there's computational irreducibility. That's why this looks complex to us. Another consequence of the principle of computational equivalence is that many of these systems will end up being universal computers. So, for example, this is Rule 110. We can let's just make a slightly different version of this. Let's say we just started off, instead of from a very simple initial condition, let's start it off from a random initial condition. And let's say, let's do this. Okay, so here we can kind of get some guess that there are all these little structures, and we can kind of imagine maybe this is making some kind of logic operations and things like that. And you can show, yes, indeed it is. Just with this extremely simple rule, we can make a universal computer. And that's a generic thing. It tells one, if we're interested in making computers out of things other than semiconductors, if we, for example, want to make computers out of molecules, it will be the case that even rather simple components are sufficient, if we set them up correctly, to be able to make things which can act as universal computers, which can be programmed just like the kinds of computers we normally have. So that's one of the consequences of this principle of computational equivalence. Okay, so one of the things that this kind of tells us is, in this computational universe of possible programs, there are just amazingly complicated things that can happen, and they happen even with very simple programs. So one of the questions we might ask is, how can we make use of, for technology, how can we make use of what's out there in the computational universe? When we think about technology in general, what are we doing when we do technology? We're basically taking things that exist in the world and kind of organizing them for human purposes. So we discover, liquid crystals that exist as materials in nature, and then we say, well, actually, we can use those to make displays which are useful for us, and so on. And so that's how we sort of think about technology in the physical world, but we can also think about technology in the kind of computational world. And what we're doing then is we're saying, let's go out into this computational universe and let's mine programs for ones that are useful to us, for ones where we have some kind of technological purpose for them. So, for example, with Rule 30, you can go mine this as a very good pseudorandom generator, for example. You can mine other kinds of things for doing image processing or various kinds of machine learning types of things and so on. And in a sense, the standard kind of neural net machine learning is a rather kind of complicated version of the same idea of going out and mining the computational universe for things that are useful to you. I suspect there's a vastly simpler way to do those kinds of things, but that's something still for the future to be discovered. But the basic point is that out in the computational universe of possible programs, there's just amazing power that exists to be able to do lots of things with computation. And in a sense, the story of AI is a story of how we can take that power in the computational universe and apply it for human purposes. And of course, there are issues about sort of how do we figure out how do we take this sort of ocean of computational ability and how do we set it up so that it's being applied for human purposes? How do we specify what we want from this ocean of computation? And in a sense, that's the mission of computational language, is to be able to do that, is to be able to say, this is how we connect things we humans care about and represent in our computational language. And that provides a bridge, in a sense, to this computational universe of possible computations. So kind of what I see, for example, Wolfram language is doing is in this ocean of all possible computations, it's defining in as crisp a way as possible those computations which we humans care about. And it's giving us a way to sort of turn our thoughts, to present our thoughts in a way that can be mapped into what's possible in the computational universe. Now, there are many kinds of applications of that. There's sort of, it's leveraging the power of the computational universe, or at least that corner of the computational universe that we humans currently know that we care about. And as we start thinking about sort of how do we deal with AI and things like this, we might say, well, AI is sort of potentially has access to the full computational universe, but a lot of what's in that computational universe is not stuff that we care about right now or that we understand. So, for example, if I were to, in Wolfram language, if I were to, for example, do automated theorem proving, let's say, I could say, find a proof. Let me actually find a good example here. Sorry, I need to pull something up here. Let's get. Let me give you an example here. Okay, this is. Let me show you something. This is somewhere here. Will probably be. Here we go. So this is. An axiom system that I found for Boolean algebra. It is the simplest axiom system that's possible for Boolean algebra, and we can go and say, let's try and make a mathematical proof here using. I've got to pick up my axiom system. Oh, actually, I'm sure it's built in here. So let me just do this. So use this tiny axiom system and try and prove this result. So what I'll get here is a proof of that particular thing. It takes 102 steps, and if I wanted to, I could say, show me kind of the data set of that proof. It'll show me all the steps in this proof. Okay, so it's great. We've proved that we can get commutativity of NAND from this axioms for Boolean algebra. The problem is, we humans don't understand this proof at all. This is something that sort of was plucked from the computational universe, but it's not something that we humans have a way to understand. It's the same kind of thing if we're doing machine learning. Let's take an example of that. Let's say, let's pick up some data set. Let's take the MNIST data set, for example, and let's go ahead and let's just take a random sample of well, actually, I'll tell you what. No, okay. Well, here, this is kind of interesting to see. Let's take a random sample of, let's say, 500 things from the MNIST data set. Let's go ahead and say, let's build a machine learning classifier. Maybe this is not going to be the most interesting thing to see, but this is just going to build a machine learning classifier based on that training data. And the question is kind of, can we understand the thing that we get out from this? I have a bad feeling, this is it's using a bunch of different methods, and it may be using a method which is sort of too simple to really show this in a nice way. I think it is. I think it's just going to use logistic regression for that smaller data set. Okay, let me just, actually, I'm just going to tell it to stop there. And it'll give us the partial result. But maybe I can show you, let me show you this. Let's say I have, let's see what's happening here. I am surprised that's not auto-completing. Well, what I was going to try to show you. Oh, here we go. Okay, so this is an image identifier. So let's say we have let's go ahead and get picture of a tiger or something. That's just based on our built-in internal data, tiger, species specification. There's a nice tiger. Okay, let's try running this image identification network on that tiger. Okay, it says it's a tiger. Great. Now let's say, how did it figure out it was a tiger? Let's go ahead and just take the first, let's just use the first 10 layers. Well, we can say, what is that neural net? And we could go and just look at that actual network. And we can see, again, it's all represented symbolically here. So this is a symbolic representation of that neural net. We could dig into it and we can see all these different layers and all these kinds of things. Now we can just say, use the first 10 layers of that neural net and see what you got. Okay, I need to turn this into images here. Okay, so these are kind of the thoughts of the neural net, so to speak, as it tries to figure out what that picture is of. And the problem is that we humans are not well equipped to understand the internal thoughts of the neural net. We don't have, in our human language, we haven't developed words for whatever it is that is, whatever feature it is that the neural net is noticing that is going to turn into the tiger and so on. So it's something where this is something that is sort of plucked from this sort of ocean of computational possibility, but it's something that is not something for which we have a human way to describe it. And so there's sort of a question when we have AI and the AIs are doing what they're doing, is kind of how do we tell the AIs, okay, do the kinds of things we want you to do, but not other kinds of things. And that kind of gets us to the idea of using computational language as a way to kind of define contracts for things. So normally we might say, well, let's put down some laws for the AI. And those laws would now be written in some natural language, English or some European language, whatever it is. But they will be written in, well, basically just natural language or some kind of legalese. But the question now is, can we actually specify that contract in a computational language? Can we use our computational language to talk enough about the world that we can say what we want to have happen in the same way that a legal contract does that? And by the way, this is something for purposes of things like blockchain. Smart contracts are sort of the beginnings of that story, and people use our technology a bunch for building those, and particularly our Wolfram Alpha technology for making kind of oracles for smart contracts and so on. But the point there is that we're able to. It's something where we're specifying things about the world computationally. So, for example, one of the big things we might want to specify is for the AIs, we might want to say, this is your constitution. We want you to be nice to humans. This is what that actually means, represented in computational language. It's the same kind of thing when you say, you've got some social network or some search engine or something, and you want to say, this is the set of things that I want to see. This is the sort of contract that describes what kinds of things, how I want to rank my content and so on. It's the same kind of thing, describing it in this computational language that's both understandable to us humans and understandable to the AIs. By the way, when it comes to, I just have to kind of show you just what it looks like to interact with the blockchain. I don't know. Let's say let's take the Ethereum blockchain or something. Let's just look at the most recent block that was mined in the Ethereum blockchain, and that's now bringing that into Wolfram language. Or we could say, let's just try. I wonder whether this will work. Blockchain token data, and let's try taking. I don't know. Let's see whether I get. I have to say a particular kind of token. So. Is that one? CryptoKitties? Yeah, there we go. Okay. So there's CryptoKitties, and that's telling us the number of holders of CryptoKitties and so on. And we can go and sort of do all kinds of analytics on blockchains and so on and use, do all sorts of things. But it's kind of just interesting to see how that flows into our language. And this is something also where we're just starting to be able to kind of push computational contracts out into that world so that they can be kind of autonomously executed there. But okay, back to the story of kind of, we have this kind of ocean of computational possibility. We have the computational language that's our way of kind of humanizing that and giving us humans a way to kind of access the power of the computational universe. Okay, there's a third piece to this that I've also been very interested in. I thought you might like to hear about, which is okay. So, what about the universe? We now know, we take something like Rule 30. We say, well, it's possible from a very simple rule to generate this complicated behavior. What about our whole universe? Is it conceivable that that's just a simple rule that describes our whole universe? And I've long wondered about that and built a bunch of science around that. And the thing that happened a couple of years ago now, as a result of what was initially a little sort of technical breakthrough, started realizing that, well, actually, you can understand in the end all of physics using as something which emerges just from a simple program. And so what this has been sort of a big excitement of recent times is actually being able to find out that physics really is computational underneath. And this has been rather a spectacular thing, because what's happened is ends up being sort of the machine code for the universe. It ends up being the thing that seems to be kind of the lowest level representation of the physical world. And it turns out that a lot of things people have done and a lot of very nice mathematical physics that people have done actually plugs into this. It's kind of the high level representation of some of what's going on, but we now have something of the machine code of what's happening. So maybe I can just sketch for you sort of the view that we now have of how the universe is set up. So the first big thing to realize is that the first sort of thing people assume that turns out not to be true is what space is. People from Euclid on, people have just sort of said space is this thing you put stuff into. You can say, I'm going to put a thing at this position, I'm going to put a thing at that position. There's no real discussion about what space is. It's just something you put things into. Well, it's similar to something like water. You might say, well, water is just a thing that flows, but we know that underneath water is made of a bunch of molecules. Well, one of the things in our physics is it turns out space is also made of something discrete. It's made of kind of atoms of space, these kind of things that are just all that they are. They're elements like points, and all they are, if you're a sort of computerish person, you might say every point has a UUID, but that's all you know about it. And then the only other thing we know is how these points are related to each other. So in a sense, we're building up this sort of giant friend network of the atoms of space, and that's all we know. And so in our model of physics, the whole universe is just this giant graph. Actually, it's a hypergraph of these relations between atoms of space, maybe 10 to the 400 of these in our current universe. And so this giant hypergraph represents everything that exists in the universe. It represents space. It represents everything that's in space. It represents electrons and photons and energy, and all those kinds of things that exist in space are all features of this big graph. Now, in itself, from the beginning, this graph isn't necessarily like space in 3 dimensions or anything else, just a giant graph. But it turns out that you can imagine a very large version of this graph where you can say, just like when you have water, it's got a bunch of molecules underneath, but overall you can say, well, it's like a fluid that's flowing and it has vortices and it obeys fluid equations and all those kinds of things. It's the same type of thing with the structure of space in these models. And what happens is the way that, so space is this kind of giant hypergraph of these elements, these atoms of space. Time then corresponds to sort of the updating of that hypergraph. And the way it works is there's some rule that just says every time you see a piece of hypergraph that looks like this, transform it into one that looks like that. And you just apply that wherever you feel like, so to speak, in this giant network. And that's the progress of time. This phenomenon of computational irreducibility kind of shows you that there's sort of an irreducible process of evolution through time. And that's and so it's then not obvious, but turns out to be the case that things like relativity, which relate space and time, are the result of kind of embedding the observer inside this system and seeing what the observer is ultimately only can observe kind of the causal relationships, the causal graph of relationships between events and so on. So in any case, but the end result is that just as all those molecules bouncing around in a fluid end up at a large scale satisfying the gas laws and the equations of fluid dynamics and so on. So similarly, from our atoms of space, the thing that emerges on a large scale is general relativity and the theory of gravity. And so the structure of this network on a large scale satisfies the same equations that we believe are satisfied by the large scale structure of space-time. So it's quite a very rather exciting thing that you can go from this very low level representation to something which behaves and shows gravity and all those kinds of things. It goes beyond that. One of the big features of physics is quantum mechanics. And one of the things about these models is when we talk about, we just update everywhere we feel like, what that means is that there isn't just a single possible thread of history, because depending on what order we do those updates, we're going to get a different history for the universe. And those different histories are represented by these things we call multi-way graphs. And the point is that, in a sense, they represent quantum mechanics. Quantum mechanics, the sort of core idea of quantum mechanics is, in classical mechanics, you throw a ball, it follows a definite trajectory. In quantum mechanics, the ball follows many different paths, and we just get to say the probability with which the ball ends up in some particular configuration. Well, it's the same thing here. There are many possible paths, many possible histories for the universe, and we only get to sample certain aspects of that. So in a sense, there is a necessary in our models, quantum mechanics is a necessary thing. One of the features of these models is, if you look at all these different paths of history, you can kind of slice across these paths of history to make something where those different possible histories of the universe are represented at different points in a space. And we call that space branchial space, the space of quantum branches. And it's like physical space, except it's not physical space. It's another kind of space. It's the space in which quantum mechanics plays out. And one of the things that's quite remarkable is that while in physical space, the main thing that emerges is the theory of gravity, the exact same theory, when applied to branchial space, is the theory of quantum mechanics, is the theory of Feynman path integrals and things like this. So it's sort of a remarkable thing. People have wondered about sort of how gravity and quantum mechanics fit together. The answer is they're actually the same theory, just played out in different kinds of space. And the interplay between those different kinds of space, you start to see sort of an interface between them when you're looking at black holes and things like this, and you can start to see sort of the interaction between physical space and branchial space. But the thing that is so that's kind of the structure of what's going on there, and so this is kind of one of the questions in quantum mechanics. There's always a big mystery about how we humans perceive a quantum world, and it's actually a little bit of a brain twisting thing that we've sort of realized about what happens in our models. So the universe is branching all the time. It's branching, it's merging, it's making this whole sort of network of histories, but we are observers of the universe, and we are embedded in that universe. And so our brains are doing the same kind of branching and merging and so on. So in a sense, the story of quantum mechanics ends up being a story of how does a branching brain perceive a branching universe? And a lot of the sort of mysterious aspects of quantum mechanics have to do with this kind of, how does the branching brain perceive the branching universe? If you ask about things like quantum computers, kind of the story of quantum computers is a story of, well, can we use these different paths that quantum mechanics can explore? That it's more explicit the way that path stuff works in our models than it has been in traditional quantum mechanics. But we can kind of explicitly see these different threads of execution of things that could be done in quantum mechanics. The problem is, okay, so you've done all these different threads of execution, but in the end, we humans want to say, we want the answer. Well, what's the answer? Well, we've got this whole giant collection of threads of possibilities. How do we corral those back to something that we can view as being the answer? Well, that's a complicated thing. And in traditional quantum mechanics, that's not something one really talks about. One just says, well, there's this measurement process, and it just goes boom, and you've got the answer. In our models, we actually know something about the dynamics of that process. And so that kind of tells one that sort of the kinds of things one might think would be a big advantage in quantum computing probably aren't, because after you get all this sort of branching parallel stuff, you then have this big effort to corral all those parallel threads back together again. And that turns out to not, in the end, be an advantage, although there are a bunch of all kinds of strange and interesting effects that occur there. Now, I could talk about one of the things that's come out of all of this is this idea of what we call multi-computation, this idea of not just having a single thread of time, a single sort of sequential thread of execution, but having something where there are many different threads of execution, and they're all happening. That we're not saying, are they happening, in parallel, whatever else? They all can happen. And the question is, how do we sample that? So, for example, in programming, we have things like logic programming, we have theorem proving, things like that, where basically you say, is there a path that gets from here to there? If there's a path, then we're a winner. That's kind of the theory of non-deterministic computation and so on. It's also in other areas, it's, for example, chemical synthesis. That's a story of chemical synthesis. You have a bunch of chemicals, you have these different reactions you can make. Is there a path? Is there a synthesis pathway that gets me from my inputs to the particular molecule I'm trying to make? Well, so those are examples of this kind of multi-computation idea. But what we've realized from the physics project is that instead of just saying, well, I want one path, there's this whole notion of all these paths turns out to be an important thing. And in physics, what we're seeing is that all these paths sort of happen in some sense, but there's an observer that has to be kind of sampling these paths and knitting together our experience from that. And it turns out that an observer that's at all like us, two characteristics of us, we are computationally bounded, and we believe we have a single thread of experience in time. We believe that time progresses as a kind of one-dimensional thread. Those two things, which I think are sort of the essence of the way that we sort of apply consciousness to thinking about the world, those two things are sufficient to take us from this kind of multi-computational mess to something where we have a definite kind of perception of what's going on in the world. And those, when we look at sort of the physical universe and all of these atoms of space and all the rewrites and so on that are going on there, the question is, how do we, from that computationally irreducible mess, so to speak, how do we deduce things that are predictable to us? And the answer is that as observers with those features of computational boundedness and sequentiality of time, that forces us to only sample those aspects of this big computationally irreducible multi-computational thing, to sample only those aspects which turn out to correspond to the laws of physics we know. So in other words, the fact that from the universe we deduce the laws of physics that we know is a consequence of the way that we're sampling the universe. Well, so it turns out, the thing that I realized only very, very recently, is there are a lot of other fields where this idea of multi-computation can be applied, and where this kind of notion of the way that where there are observers of what's going on that observe, that sample those different things. So, for example, there's a meta-mathematics is one area where one's trying to understand kind of the structure of the space of all possible mathematical theorems and so on. That's a bit abstract. I'm happy to talk about that if people are interested. I think there's some very important kind of issues about the sort of philosophy and foundations of mathematics that come from that. But at a more pragmatic level, one can even talk about something like molecular biology. In molecular biology, you've got all these different reactions that can happen, and they essentially form something like a multi-way graph. And one can ask, well, what kind of observers are there of this kind of molecular computation that's going on in a chemical system? And one kind of observer is the kind of thing that we're used to doing, of just saying, what's the concentration of each chemical and so on. But another kind of thing we can do is to say, let's look at this whole dynamic network of what's happening and see and try and use that as our representation of what's going on. And so what is the chemical observer? What is the molecular biology observer? It could be just us measuring chemical concentrations. It could be some feature of some cell where one's seeing, how particular molecules bind to some membrane and things like that. And it could be, I think, that something sort of very big in biology could end up being the fact that when we represent kind of biological processes, molecular biological processes, in the right kind of way, that there's sort of very different ways in which those processes occur. Like, for example, when DNA was discovered, when the function of DNA was discovered in 1953, one went from just there are these molecules made to this idea that a single molecule can contain all kinds of digital information. I think there's a likelihood now that something else that one can think about in molecular biology and so on is, well, there's this whole dynamic process that we have to look at with all these different molecules that is not just a count of not just what species of molecules exist, but what is the detailed dynamics of all these molecules, and that too is a way of sort of storing information. And that's interesting if you're interested in molecular scale computing and things like that. It's also interesting if you're interested in things like how the immune system works and how kind of the space of possible antibodies. There are 10 billion different kinds of antibodies that we have in the shape space of possible antibodies. What's the analog of the things we know in physics, like general relativity and gravity and things in the shape space of antibodies. And that's something which I think has the potential to give one a sort of physics-like theory of something like the operation of the immune system, which will be an exciting and important thing to have. And these kinds of ideas also, I think, apply to areas like economics. It's like, well, what are the atoms of economics? I don't know this for sure yet, but I think that we can think about the kind of transactions as being sort of the lowest level elementary events in an economic system. And there's sort of the traditional view of an economic system. Well, you can say there's this giant network of transactions that are happening. And the question is, how do we parse that network? How do we understand what's going on in that giant network? And for example, we have ideas like things have a value. It isn't just the case that there's a chain of sort of barters that are happening to get from one place to another. Instead, we can say this thing has a value, and that defines what kinds of transactions will happen and what will not. So this kind of idea of multi-computation, which has come out of physics, come out of our understanding of fundamental physics, which in turn has come out of our understanding of computation and the foundations of computation, I think this has the chance at this point to define a model that can be used for these different kinds of areas. And one of the things that does is it gives us a whole nother way to sort of make use of this computational universe. So we've had this kind of approach to the computational universe where we have the kinds of things that we are representing right now with our computational language, but there are things which are sort of a whole nother area of things that can be represented and things that we have a chance to be able to pull into things that we humans can understand and reason about. And so that's, for example, one of my current projects is trying to understand how to turn this multi-computation idea into something which can be represented in a kind of computational language type of way. So I think I'm going kind of long here, but let me just sort of finish off, and then I'm happy to try and address some of these questions and lots of things that have come in here. So I'm happy to try and talk about them. The big picture here is what does computation make possible? What exists in this computational universe of possible programs? Well, it's a very rich universe of possibilities, rich enough that our universe is in there.
Hey, folks. It seems, I'm so sorry. It seems we have a slight internet connection issue. Stephen has informed us earlier that in his area there have been a few internet outages. So it seems that he has dropped off. Let me just quickly check with our tech team if we're able to bring him right in. He had said he was plagued a little bit with this. So just give us 30 seconds to check in. I think from the audience engagement and hop in. Thank you so much, everybody, for a lot of great questions. It's truly engaging. So I get the signal he's back. So you can see Stephen again.
Nice.
Thank you so much, Stephen, for rejoining us.
Let's see. We were just talking about kind of the big picture of sort of what's possible in the computational universe, being able to make this bridge to kind of what we humans understand through computational language, and then realizing that sort of the universe really is computational all the way down. This idea of computation is powerful enough to represent our whole physical universe, and then understanding what other consequences this idea of computation has. And in a sense, a big picture of my kind of life and times has been trying to actually build the practical tools to make use of what's possible computationally. All right, I see lots of questions and comments here, so let me start off here. Let me take these from the top. Andrea is asking, the field of artificial life and genetic algorithms has become much quieter. What is my opinion about those branches of AI and so on? Well, I think this notion of artificial life. What is life? what is the kind of essence of what makes life? Well, I think one of the things one realizes is the generalization. Life on Earth, we can define pretty easily. It's got RNA, it's got cell membranes, it's got those kinds of things. What is the generalization of life, so to speak? And what I realized ages ago is that the generalization of life is just sophisticated computation. You know, when you run a cellular automaton and you get something like this is kind of generalized life. And so it's not clear where the boundaries of kind of, our type of life versus generalized life actually lie. And so I think when we're talking about artificial life, when we go beyond kind of the life that's sort of Earth-like life made with amino acids and so on, we end up just sort of talking about this big picture of computation. And by the way, when we're talking about kind of alien intelligences, so to speak, where this principle of computational equivalence kind of says lots of things are intelligent-like. Whether it's the weather, whether it's a cellular automaton, whether it's some piece of physics, these are all doing things which are computationally equivalent to our brains. And so they're sort of intelligent-like. The question is, are they aligned enough with us that we can kind of understand them? And in this kind of models of physics, one of the things that's emerged is this notion of rulal space, which is kind of a notion, let me not try and explain it in total detail here, but basically it's kind of a different points of view about our universe. We kind of have different ways to understand how our universe works. And in the end, I think that we can understand there is only one universe, but there are different rulal reference frames. There are different ways we can understand our universe. And it's kind of like we are at a particular place in physical space. We're not on Alpha Centauri, we're here on Earth. And that gives us a certain perspective on our universe. And similarly, we're at a particular place in rulal space, which corresponds to the particular sampling of our universe that's associated with our senses and our ways of making theories about the universe and so on. And so that kind of gives us a perspective. When we talk about alien intelligence, it's kind of like how far away might we be in physical space and how far away are we in rulal space? How close are we to being able to understand how that works? So I think that's kind of the picture of kind of what that's sort of my picture of that. I think that there's a different issue, which is kind of making synthetic biology and understanding, can we make from the raw material of biology, can we make interesting kinds of things? I would say that one of the things that's come out of this principle of computational equivalence, coming out of this emerging potential understanding of chemistry, is there may be other ways to do molecular scale computing other than the one that biological evolution has delivered for us. And that will be an interesting thing. It will also be interesting to interface the other potential ways to do molecular scale computing with the one example of molecular computing that we have, which is us and biology and so on. I would say in terms of things like genetic algorithms, one of the things, again, that comes out of this idea of multi-computation is evolutionary biology and biological evolution there is a kind of easy description of Darwinian evolution, but there is not a good formal description. There's not a good way to understand, why do species happen? Why are there the number of species that there are? I have a slight suspicion that with these ideas about multi-computation, that it will be possible to understand that, and possibly even things like the formation of species is like the formation of event horizons in physics and things like that. I'm not sure how that will work out, but I think that may give us a bit more insight about sort of the concept of genetic algorithms and the exploration of this space of how you move around in the space of possible programs and how potentially Darwinian evolution moves around there. See, one of the issues is Darwinian evolution is a story of incremental change. A bone gets longer, a bone gets shorter, the animal is able to eat things or not eat things or whatever else, but it's a very incremental thing. It's kind of like using calculus to make small variations of things. What tends to happen in this computational universe is you go from one rule to another and there are dramatic changes. So this notion of incremental change doesn't work quite so well there. Question, another one from Andrea. As a young engineer looking to join a company, which company would you join and why? Depends on you. It's, my company is like 800 people or something, and we do kind of we've been in this wonderful position of being able to do very innovative things for the last 35 years. But our company has particular kinds of people that thrive in our kind of culture of people who are good at figuring stuff out and working independently and sort of directly communicating things and delivering high quality results and things like that. And another company, you might be much more structured, and it might be much more, you know exactly what you're supposed to do, and it's just a question of executing that, rather than the more free form kinds of things that you would find in a company like ours. So I think it really depends pretty much totally on you and and finding that match between sort of your interests and abilities and what a company is doing, its mission, its culture, and so on. And that's always it's an interesting thing. I know, as a CEO for a long time of my company, one of the things that I sort of pride myself on is the fact that we have a lot of very talented people from around the world. We're a very geo-distributed company. I think I felt a bit guilty that this pandemic had so little effect on us because we were already sort of scattered all over the world, so to speak. But the thing that had is I mean, we're let's see, I lost my train of thought here. I was talking about kind of what, in our company, one of the things that I sort of found interesting and fulfilling is there are all these different projects. There are all these different kinds of things we're trying to do, and there are all these talented people. And the question is, where is there a match between the projects we might do and the talented people we have or we can get? And that's sort of the CEO problem, is kind of matching those things up. And sometimes it's like solving a science problem. It's very satisfying when you can see there's this set of abilities this person has, and there's this project we could do, and gosh, you can match them up, and then something wonderful happens. But that's doing that for yourself and identifying kind of what company and so on has the right kind of culture and interests is an important thing. I mean, people also, there are features of people like, different time scales that people operate on. It's like there are people who are best doing a 15-minute project. If you're doing technical support or something like that, and, you've got some engineer who's going to call up and says, I'm building this rocket and I need to run this piece of code and it isn't working and I need the answer now. That's the 15-minute timescale person. And then there's the person who's like, I need to set up a giant structure for any project I do, and it's going to take me 2 months to set up the structure. And, if you feed me a 15-minute project, I'm going to take 2 months and 15 minutes to do the project. And there are different kinds of things, in lots of R&D that we do. Some of the R&D we do is like 5-year timescale R&D and beyond. And that's a different type of person or a different stage of life of a given person from the person who's like, I want a stream of things that are going to take 15 minutes. So these are all things that are sort of, you can identify in yourself. And then there's a question of sort of how does that match with what a company provides? Let's see, a question from Bogdan. Does Wolfram language support distributed ledger applications? The answer is yes. We're working with lots of blockchains built in. Well, we've been blockchains like Cardano and Tezos and the standard ones, Bitcoin and Ethereum and so on. We're doing lots of stuff with these. Lots of cool and fun things with NFTs and so on, including a lot more to come there. We just did a cellular automaton NFT auction. It went surprisingly well. It's just kind of fun. Let's see. Question from Ninad. Let's see. Okay. Is there a computational technique that will improve the hashtag that we use to investigate human migrations and possibly find out when a basic word or syllable was first spoken and became a term? That's a very interesting issue. The issue of linguistics and the evolution of language. In fact, this is another application that I've been thinking about for this multi-computation idea. Let's say that we could record every conversation that was going on everywhere, and we would see certain words and they're used in certain contexts, and we could kind of imagine that every sentence spoken is an event. And the input to the tokens that are input to that event are the words that go into that sentence. And those words were used together in that sentence. And that's kind of an event. And we can imagine kind of the knitting together of the structure of a language in terms of that whole series of events that occur in words being co-spoken in sentences and so on. And from that, you can start to ask, can we do a sort of physicalization of that kind of setup? Could we ask things like, well, there's this word and it propagates through unchanged, but then its path ends. It's like that word goes extinct. It's like in physics, it will be like a space-time singularity in a black hole. or a word splits into two. And we've done a few experiments with this with our machine learning system, and it works rather nicely. You can kind of start seeing the different meanings of a word kind of arranged in different places in meaning space. People sometimes think meaning space is something that can be represented as a kind of linear vector space with just arithmetic coordinates and so on. I don't think that's right. I think it's more complicated than that, more like kind of branchial space in our models of physics, which is a more complicated mathematical structure that we don't fully understand yet. But I think this idea that you can kind of see the evolution of a language as kind of the relationship between words is kind of like this branchial space, and you're kind of seeing the evolution of the language as you see the evolution of space-time, for example, is an interesting idea. And I think that from a we obviously don't have all that data right now, although there's plenty of data that's being captured. I mean, I myself happen to be a person who's recorded a lot of data about myself. Every, keystroke I've typed for who knows how long, I don't know, 20 years or something, every piece of email for 35 years, all those kinds of things. And so, for example, one thing I've actually been meaning to do, and maybe you remind me about this, is I want to know when I first used each word that I've used. So in other words, and I've looked at that occasionally, it's like, when did I first use the term multi-way system? 1992, I think, was the answer to that. When did I first come up with the name of some Wolfram language function? I've answered a bunch of those. But I'm kind of curious for myself, what's been the evolution of my use of language over the last 35 years? And I have all the data to answer that. And I just need to do the work, which won't take very long. There are other things to do. Let's see. Question from Christian Buddha. What field would I suggest a student enters if they want to have an impact on the world? Computer science, physics, medicine, biology, or any other? Okay, look, here's the basic rule about fields and the evolution in the world. At any given time, most fields are kind of in a cruise state. There's incremental progress. But every so often, usually there's a methodological advance, and some field will erupt, and there will be rapid progress for some amount of time. So, for example, this happened with machine learning over the last 5 to 10 years. And there'll be there's sort of low-hanging fruit to be picked because there's a new method, there's a new idea, there's a new kind of thing you can do. It's happening with blockchain right now. And what happens is there's a period of 5, 10, maybe a little bit longer years when there's sort of a rapid growth of that field. So, for example, back when I was a late teenager, I worked in particle physics, and it was in the late 1970s. And that was a time when there had been methodological advances from quantum field theory and so on. And particle physics was in a state of rapid growth. It was in kind of an explosion of possibilities. And so, I did a bunch of particle physics, and I wrote papers when I was a kid that still get used today because I was involved in that field at a time when it was having this kind of golden period of expansion and where there was low-hanging fruit to be picked, and I had the pleasure of picking some of that low-hanging fruit. So typically, the sort of the general rule is that if you want to have sort of the highest leverage impact is in fields where there is a rapid expansion going on because of typically some methodological advance. And usually once there's been a methodological advance in a field, it can be 50 years, 100 years or more before another methodological advance happens and it re-erupts into something exciting. For example, and so one of the things to do is sort of pick these places where there are methodological advances going on. But it's always very confusing because if you say, is there a department of X, where X is some field where you think there's a methodological advance? Well, there won't yet be a department of X in your university because it's a new field, and it takes decades for there to be a department of X at your university. So it's kind of a challenging thing because you have to be sort of entrepreneurial in thinking about these different fields to say, well, this is a field that I can enter. And by the way, new fields, there's typically much less depth of stuff that you need to know to be able to contribute to the front lines of that field. So, for example, right now, I would say, well, the one area where I think the idea of computation is a sufficiently big idea that it probably has a 50 to 100-year ramp. And we're about in the middle of that ramp right now. So the idea of apply computation to everything, that's a big idea. And that's an idea that has lots of mileage. And essentially, the way to think about it is if you have a field, archaeology, zoology, whatever, you say, is there a computational X field, computational zoology, computational archaeology? A good heuristic for finding a place to sort of enter right now is look at one of those things which doesn't exist yet, or which just barely exists. That's going to be a growth area, because this idea of computation is at least on a 50 to 100-year ramp of being able to make use of that methodology in all these different places. So this idea of sort of computational X for all X, this is a big idea, and this is an idea that people can get involved with for a particular X that, for whatever reason, raises your interest, whether it's computational medicine or whether it's computational, the lots of different possible things. I think that, what I've been trying to do is build the language that supports computational X. Just as mathematical notation supported mathematical X, the mathematical sciences, so now it's sort of a bigger problem is, can we build the language to support computational X? So I have to say, I should make a pitch for learn our language, because it allows you both to, as a practical tool, to actually do computational X. But more than that, it's a tool for thinking about computational X and being able to formulate your thoughts in such a way that you can kind of do computational X. Now, I will say that something that is, for example, this whole multi-computation idea, which I just wrote something about like a couple of weeks ago. This is going to be a big idea. This is going to be a big methodological advance that's going to end up affecting lots of fields. I don't know exactly how quickly, a few years, I think it will go comparatively quickly. Some things go more quickly than others. I've said that some of the sort of core ideas that are in Wolfram language that are basically 40 years old are still sort of slowly getting absorbed. I think this multi-computation idea is probably going to get somewhat more rapidly absorbed, just because of the dynamics of these different fields and the ways that one can deliver kind of definite results from those. I think another, I will say that actually probably today, maybe tomorrow, I'm about to post something which is actually mentions two new fields that didn't exist before. And one of them is what I call meta-modeling, and the other is what I call ruleology. And what these have come from is, I mentioned complexity. Something I've worked on, was interested in for 50 years now, and was the thing that sort of drove this big book I wrote nearly 20 years ago called A New Kind of Science. Next year is the 20th anniversary of that book. And so I've been kind of thinking about sort of the effects of the things that were in that book, and the sort of transition to making models using programs instead of equations and so on, that book was kind of in the middle of. And one of the things that's come out is there's this sort of field of complexity, studying complexity, that I guess I was very much involved in initiating in the 1980s. And I've sort of asked, what happened to that field? And I'm kind of trying to understand, what's gone on with that. And I think it got very applied. And I realized that there are a lot of foundations of complexity that are important. And the question is, what are the real things you should figure out? And I realized that you can sort of break it down. Meta-modeling. What is meta-modeling? Meta-modeling is the idea of, you have a model of something. You have a model for, I don't know, snowflake growth, or growth of trees in this, that, or the other way. And the model is made for that particular purpose. And it's got all kinds of complicated stuff about actual tree leaves and whatever else. But the question is, what is the meta-model underneath that model? What is the raw, minimal model that is that thing? Is it a cellular automaton? Is it a Turing machine? Is it something quite different? What is the raw underlying model? And so I think there's a very interesting sort of scientific direction, meta-scientific direction, of taking models that people have made and saying, what are the core underlying things that are going on here? It's actually a problem very much like language design. But anyway, that's a kind of a new thing just emerging. The other thing is what I call ruleology. And so when I was showing you like Rule 30 and things like that. This is a story of, you've got these simple rules, what do they do? And that question of what do simple rules do is a very core, very basic scientific question. And over the past 40 years that I've been doing these kinds of things, and other people have done things in this area as well, a lot of things that people have done, often building on stuff I've done, that is kind of like answering this question: what does this very pure, very abstract, very specific rule do? And people have written these things. And what's really nice about these things is they survive. There's some detailed model, and it's got all kinds of detailed hair, and that kind of goes by the wayside. But this thing, which is kind of like pure mathematics, this kind of pure question, what did that simple rule do, that's a thing that very much survives. Just like, you can find from ancient Egypt, people were making little icosahedral thingies. And, you pick up an icosahedron from ancient Egypt and it's like, this is a very modern thing. It's an icosahedron. It's as modern now as it ever was. And it's the same thing with kind of studying these simple rules. So I've kind of been trying to formulate what is this field, which I've been doing myself for like 40 years, and other people some other people have too. How do we turn this into a kind of systematic field of what I'm calling ruleology? That's kind of a new word that I just coined to represent this field of studying what do simple rules do. And that's a place where right now there aren't departments of ruleology yet in universities. One day there'll be a first professor of ruleology, so to speak. But that's a field where I know that there's a huge amount of low-hanging fruit to be picked. It's also, like many fields, it's people will say, well, that's nice, but why do we care? Well, at this point, we have a lot of evidence that there's reasons to care. Our physics project is a really big one of those, but it's something where it's a sort of emerging field, and these emerging fields are usually the place where they're the place where high growth happens. I mean, people sometimes say it's all interdisciplinary kinds of things. What does that mean? Interdisciplinary means it wasn't one of the well-developed fields. It was something that was between well-developed fields. But the most important thing is it was something that was new and different and not part of the kind of the cruise phase of an existing field. So that's my little bit of commentary on that. Let's see. Well, maybe a few more things here. Let's see what. It's a question from Bogdan. How far off are we from artificial general intelligence, and will it be possible? It's a question of how you define it. It's like, I remember back 40 years ago or something, people were saying, when we have the ability to do symbolic integration, then we will know we have artificial intelligence. When we have the ability to recognize an image, when we have the ability to do general question answering, like in Wolfram Alpha, then we will know we have artificial intelligence. Each one of these things ended up being done with, quotes, just engineering. But in a sense, our brains are just engineering too. So the question is sort of, what do you want from your AI? People like, for example, when people use Wolfram Alpha to make Turing test bots, they lose because you just ask the Turing test bot all kinds of weird questions that we can readily answer with Wolfram Alpha that no human will be able to answer. So it's a question of, is that a valid kind of general intelligence, or did we miss because we went too far and we went beyond what humans can do? So I think it's a complicated kind of definitional question, what we really mean. And, this issue of there's all this sort of capability out in the computational universe, which part of that, there is plenty of capability out there that far exceeds what we humans can do or think about. The question is, what parts of it do we want to kind of reel in and say, these are the things that we want to consider being artificial intelligence that we're building for our purposes? So I think it's sort of a definitional issue. Let's see, a question here from Jennifer. How far are we from taking the leap from transcriptional translation to being able to proactively and largely in real time decode languages like the universal translator and so on? Well, it's been interesting to see the advance of it. The question is, when you have a neural network, what is it likely to be able to do? I mean, neural networks are essentially, they're interpolating data using these very complicated functions that are essentially learnt from data. And the question is, what works by just interpolating data? Now, a thing to realize is there is something like doing mathematics. It doesn't tend to work that well that way. Something like recognizing images, it works rather well. But in a sense, okay, so one issue is the environment that we're used to dealing with that has tigers and teacups and all this kind of thing in it. This is an environment that we humans have gotten used to, and our brains are pretty good at decoding. And I think one of the things that we're seeing with neural nets is they are similar enough in their architecture to brains that the kinds of things we humans find easy to decode are things they also find easy to decode. We could imagine an alien intelligence which has a very different world where it's making use of very different structures, where maybe the neural nets that we have will be hopeless at decoding that. In fact, I think that's true in areas of mathematics where, just try adding numbers with a neural net. It's not very easy unless you pretty much put it in advance. it's you can get a certain distance in sort of doing, I don't know, integrals or something, but it gets stuck very quickly. After it recognizes a few patterns, it gets to the point of being able to sort of the elementary student who can recognize a few patterns, but it can't really like figure the thing out. It's just not the kind of thing that you can sort of interpolate with a neural net. So I think the success of things like neural nets is partly a story of what it is things we can do. Neural nets are similar enough to us that they can do some of the same kinds of things we can do. It's interesting and non-trivial when neural nets can do things like figure out protein folding, because that's not something that has any human connection. Something like language translation, it does have a human connection because we humans can do it. And so if we have something which is architecturally similar to humans, we can expect that it's more likely to be able to do it. Now, the one question is, we have, giant corpuses of, that come from the European Union having translated, pieces of legislation into gazillion languages, and we can see all these parallel texts that we can train on, or computer manuals, which are in many languages, which you can train on as samples for language translation. An interesting question is, if we're presented with, whale songs or something, some alien language, can we decode that alien language? That's an interesting question. I'm curious about the answer to that question. I do not know. I think that in a sense, one should be able to. It's sort of shocking that we can't yet talk to the animals, so to speak. We should have been able to record enough stuff about the sort of the responses and environment of animals that we should be able to tell what's going on. Now, of course, one of the questions is, you say, well, I'm going to talk to that whale. What are you going to say to it? Is its model of the world close enough to yours that you'll have anything to talk about? Or is it going to be trying to describe these weird patterns of fluid dynamics that we humans have never paid attention to and didn't know existed, and so on? Or is it going to be able to discuss, is it going to discuss philosophy, so to speak, in the same way that humans do? This is one of these questions about sort of distance and rulal space, the way that one is, how close things are in terms of one's way of describing the world. So I think it's a very interesting challenge, and one that of sort of, can we, in a sense, it's like science. In a sense, the knowing, is there a decoding of whale songs, is kind of like saying, can we decode the language of nature to be able to make scientific laws for something? But it goes a little bit further than that. And that's kind of but in the case of scientific laws, we don't imagine that at the end of it, it's trying to say something like humans say something, but we do kind of imagine that whales or ants or whatever else might be saying things that are a bit like the kinds of things that we're used to talking about. And so we might expect some more direct kind of communication there. Let's see. There's a question from Vlad here talking about tracking productivity and so on. How do I go back and review information? I have to say, I track only things that I can track without having to think about tracking them. Anytime I actively have to do something, I'll forget to do it, or I won't get around to it. I can't be bothered, or whatever else. But so I've passively collected a huge amount of information. And every so often I'll go do a study of some particular thing I'm interested in. Like, for example, one that I keep on meaning to do, and I've got the data organized for this, and I've had it for a few months, and I just haven't done it yet, is the following question. So, I know every time I've gotten sick in the last 20 years, not very many times actually, so the data is rather sparse. But my question is, what caused me to get sick? Was it because I went out to some event with lots of other humans? Was it because I went on a plane trip and changed time zones? Can I tell what is the actual trigger, the most likely trigger for me personally to, get a cold or whatever? And so I've sort of been curious about that. As the world starts opening up again, I might be able to answer that question for myself. Maybe it's the case. I don't know. Anecdotally, I have to see. Like one thing I did notice was for myself is that if I'm going to run a fever, about a day before I run the fever, my heart rate goes up, which is sort of interesting. And I don't know what that, I haven't yet had a chance to really use that predictively, but that's the kind of thing that you start to be able to learn. Unfortunately, or fortunately, in that particular case, I don't have enough data to really make some definitive statement. But, there are questions like, oh, I've changed my computer keyboard. Do I type faster or slower on this keyboard? Okay, that's easy to answer. Do I, these other kinds of questions like this, I'll have sort of random questions that I'm curious about myself. And then it becomes easy. All this data is accessible, through systems that I have in Wolfram language. It's actually mostly in our data drop, which is just a place to keep data streams. And so I can just pull up from my data drop, from data bins in the data drop. I can pull up, my step count as a function of time in a time series, and then I can correlate that with this or that. And I think this, when I was sick, is probably based on, when are there 0 steps? When did I have a fever measuring app thing? When did that go up? When did I not have meetings on my calendar? Whatever else. There are a variety of ways to get that. So I tend to go in and look with Wolfram language always, because that's really the most flexible data science system, I think, that kind of exists. And sometimes I'm using machine learning. Sometimes it'll be like I've scanned all the paper documents that I have, about 250,000 pages of that, and I wanted to know when was my top paper production time. And that's a question of looking at those documents and picking out the dates on all those documents, and that's kind of an OCR and machine learning type thing. The answer to the question is 1984 was my peak year for making paper, producing paper, so to speak. After that, I kind of went digital, so to speak. Let's see. There's a question from Bogdan. What did I believe 10 years ago might be possible that I now think isn't possible due to limits that I didn't understand before? It's an interesting question. I have to say, I think that a lot of things that I didn't think were possible turn out to be possible as one makes some of these particularly methodological advances. But I would say that some things there's some things about kind of the absorption of ideas in the world that are just so bizarrely and frustratingly slow. And there are things where it's like, surely people will understand this. But no, it takes another 30 years, 50 years, whatever, for those things to get understood. And it's sort of sometimes there are these processes that are very inexorable, like the things I did in my New Kind of Science book to do with modeling the world using programs rather than equations. There was no doubt that was going to happen. It was simply an inexorable process. The only question is, how long would it take? The answer is, it happened over the course of about 20 years. Something like understanding, symbolic language and understanding kind of the kinds of things that are the core of Wolfram language. Well, we're at, about 40 years and counting, and it's sort of a process where many people use it, but I think the true understanding of what's going on is slow. Now, there are things where I personally, like this idea of multi-computation, I had kind of versions of that idea 40 years ago. In fact, there were things that I was really stuck on 40 years ago in terms of language design that I now realized were possible, that I now realize were kind of blockages that I only realized 40 years later how that actually works. And there are plenty of things, for example, my view of mathematics and the foundations of mathematics, things that I've long believed were the case, I've now realized don't work that way. And there's a sort of different understanding that emerges. But I would say one of the things that I've been perhaps, that haven't happened the way that I might have expected, a lot of things about a sort of understanding of science and its significance and so on. I mean, a thing which is very notable to me is looking at kind of the way that science has engaged with things like this pandemic. It's not very encouraging to scientists, so to speak, because it's kind of like it gets so enmeshed with social issues and politics and so on that whatever science there might have been underneath there is long submerged, so to speak, and that makes it hard to sort of see how one disentangles those things. And once things get engaged in that sort of world, it's very hard to just say, well, the science just goes this way, and it's like, well, but that has this this entanglement and this other entanglement, and that's a way that things get blocked. But it's an interesting question. I'm not sure that's probably, if I think about it more, I'll realize other things. Well, there's a question from Jennifer about, since I published New Kind of Science, what things have I discovered that fundamentally changed my insight into life, the universe, everything? This whole idea of multi-computation that was already in NKS, but it was kind of a footnote there. And what I've realized now is it's really a big story. And in fact, if we look at the history of science, I think there have been sort of 4 big epochs of modeling. The first was kind of ancient Greece. People would just say, what's the world made of? Oh, it's made of atoms. Oh, it's made of everything. It's made of water, whatever else. It's what are things made of? What's the structural way of modeling things? Then the next kind of big phase was the mathematical phase in the late 1600s, and that was kind of everything is an equation. Then the next kind of big phase, 1980s, something I was much involved in is thinking about things in terms of computation. And I think now we've got another phase, which is this multi-computation phase. And we can kind of characterize these phases in terms of their view of time. The structural phase, time wasn't a factor. It's just what are things made of? The mathematical phase, time is just a variable. You can kind of slide it back and forth however you want. The computational phase, time is this actual progress of computation, but it's just a one-dimensional thing. It's a single thread of time. And then in multi-computation, time becomes this multi-threaded kind of thing. And to know what happened, you kind of have to have an observer. So those are things that has led to a bunch of new understandings. I just mentioned my view of the foundations of mathematics has changed recently, and in a rather interesting way, which hopefully I'll be able to write about. Let's see, a question from Andrea. What do I think a 100 trillion parameter natural language processing model would look like, and when will it be possible? I think it's a good question. We don't have a very good meta theory of machine learning. I have a slight hope that this multi-computation idea might give one a better way to think about kind of the big picture of machine learning. It's like when you do machine learning, you are learning these attractors. You're kind of, what counts as a dog? What is the space of pictures that all are interpreted as a dog? How do we characterize that space? How do we characterize training to get to that space? We don't really have a good kind of large-scale meta theory of machine learning. And I think that will help us to understand what's possible there. But the other thing we've got to understand is something like natural language processing. What really is natural language? What is the thing we're trying to learn there? And that's, again, something which, again, I'm sort of hopeful that this kind of new paradigm is going to give us more insight into. But at this point, I don't really know the answer to that. I mean, I think the thing that, for example, for Wolfram Alpha, we're doing natural language understanding. For many years, people had not been able to do natural language understanding. The thing that was what happened? Why were we able to do it in Wolfram Alpha when people had failed at doing that for 50 years before that time? The answer was because we weren't abstractly trying to understand language. We had a target. We're simply trying to translate human language into our computational symbolic language. And so that was, and also that computational symbolic language has lots of knowledge of the world. And that's what made it possible to do natural language understanding. Now, when it comes to other kinds of, how far can we get in natural language understanding? Well, that's really a story of this computational discourse language, symbolic discourse language, the question of kind of how much can we represent in the world computationally? It's a question of, can we take our natural language and translate it to an underlying sort of computational language that we can then compute with? And the answer to that is yes, I think we will be able to do that. Will we be able to translate every piece of poetry? No, we will not. Because there are things that are kind of human context that are very much tied into the specifics of human history that are not things that we will be able to get a kind of a pure computational representation of without, in a sense, it's like computational irreducibility. The only way we can represent that is by knowing the whole history, and that we will not be able to translate. It's sort of a meaningless thing to say. It's like saying, how would you model this thing? Well, you just have to watch what the thing does. How do you understand this poetry? It's kind of embedded in this whole framework of history that led to it. Let's see, Jennifer is asking, climate is changing, weather is more unpredictable. I don't know if it's more unpredictable. Have you really looked at that data? I don't know if it's more unpredictable. We looked at this at one point. I haven't looked at it in a few years, but weather forecasts had Gaussian errors, and they've had Gaussian errors for a long time, and I don't think they're getting any bigger. So this question, for example, can machine learning help weather prediction? We've wondered about that. We do a lot of stuff for weather data in Wolfram language and so on. We didn't manage to make any real progress on that. I mean, one of the things to understand is, what is a weather model? Well, it's a model of certain aspects. Things are measured about temperatures in different places. There's some satellite measurements, things like that. They all go into something which is a representation of the equations of fluid dynamics in the Earth's atmosphere. I actually don't know. I mean, I invented a technique for doing fluid mechanics, which was based on cellular automata, actually, that's used for computations at sort of small scales, particularly when the geometry of the system is complicated. I actually don't know whether those techniques have been used for weather forecasting or not. I can imagine that when there are complicated things about topography and clouds are a terrible thing for weather prediction and climate modeling in general. They're just a really hard thing to model because they have such a complicated structure. It's an interesting question whether one could use even these early techniques that I made for fluid dynamics for that. I actually wonder, as you're asking this question, one of the things that's come out of our physics project is when you are trying to solve the Einstein equations for space-time, the way that you do that right now is by numerical analysis, by numerical computation on digital computers. And in fact, our models provide probably a better way to do that than people have had before. That kind of works up from the bottom, up from this kind of structure of atoms of space, and reaches kind of up to something that approximates the Einstein equations, rather than taking the Einstein equations and making this kind of hacky discretization of those. So it's an interesting question whether similar techniques could be used in things like weather prediction. That is an interesting question, and somebody should investigate it. I will say that the typical way weather forecasting is done is you have a certain number of measurements, but they're not sufficient to completely determine the state of the fluid. And they're not even then, there can be quite sensitive dependence on different parameters in the measurements and things like this. And what's typically done is people run, 12 models or something. And then when it says, there's an X% chance of rain, that's because 3 of the models said it would rain and 9 of the models said it wouldn't rain or something. And often different services will pick up those ensemble models differently. But those are some kinds of approaches. And I think it's an interesting question whether in fact, one of the things that's very paradoxical is if you measure more accurately, things will look more random. Because if we didn't know the precise temperatures and things, it's like, oh, well, it's more or less the same, et cetera, et cetera, et cetera. By the time we've got very precise measurements, we can see it bounces up and down in this or that way. It's then a very quantitative question. And I have not looked at this question in probably 5, maybe 10 years. About variations of what's actually true about would actually be a really easy thing to study in Wolfram language if we had more time here, which we don't. I would try and do some sort of real-time explorations, but it's an easy thing to study because we've got all this weather data going back to the earliest weather data that's recorded, and you could just go look at this question of whether the volatility has increased or not. I'm going to guess it hasn't, but we'll see. Let's see. Okay, we're coming pretty much to the end here. A question from Alex about consciousness. Well, I've written a bit about consciousness, and I talked a little bit about that here today. I think one of the things that I've realized is that consciousness and these features of computational boundedness and sequentiality and time, they are very important to our perception of the universe and driving us to the laws of physics that we have. But there's more things to say about that. Let's see, modeling of the brain. Yes, there are things, actually, a piece I wrote recently about multi-computation, there's a section in there about neuroscience. And I don't know, haven't made that much progress there, but I'll just make one comment that I think that sort of our conscious thread of experience is kind of like classical physics. It's kind of like this is the main thing we think happened. Quantum effects are more like what's happening in kind of the unconscious mind of other things bubbling around that aren't the thing we thought happened, but are things that somehow contribute eventually to what happened. So that's kind of a little bit of an insight there. Okay, let's see. There's a comment from Rob here. Let's see. There's kind of complicated set of issues here about simulated universes. And I mean, the whole point of our model of physics is that it agrees with the things we know about existing physics. And there are things where we don't know why it works that way in existing physics. We have been able to explain kind of why it works that way. There is more to explain about the specifics of particular elementary particles and things like that. There's also more to the thing that's always nice in theories is where there's a big shocking surprise of kind of the theory predicts this, but nobody thought to look for that before. And when you look for that, by golly, it's there. There are some things to do with dimension fluctuation in the universe, dimension fluctuation in the early universe, some features of maximum entanglement speed in quantum mechanics. These are effects that are kind of bizarre, unexpected things that come out of our models that we're kind of hoping might actually be accessible to experimental investigation on a short timescale, but we're not sure there yet. I think when it comes to things like why this universe and not another, why these initial conditions and not other ones, that's something that, well, there's a whole complicated story to do with the universe of all possible universes and the fact that something sort of beyond what I've talked about here, a thing that I'm calling the ruliad. It's the sort of the ultimate universe represented by all possible rules for the universe. And that thing is a thing in which we exist in a certain place in physical space. We exist in a certain place in rulial space. And our view of the universe, there's only sort of one universe, but our view of it is based on where we are in that kind of ruliad object. And this question about initial conditions is all tied into that. It's all tied into sort of where we sit in the space of all possible ways to observe the universe. This is a somewhat complicated set of concepts. There's a thing that I was really surprised I had something to say about was this question of why does the universe exist? Why is there something rather than nothing? Why are these formal models actualized? And I leave it, I wrote something about that a few months ago that I was really surprised was possible to say, but I think we actually now have a serious understanding of kind of why the universe exists and some of the implications of that idea, and that's tied into what Rob is asking here. All right. I think we went way over time here, but there's a lot of very interesting questions. Thank you for those. And I had some good ideas, actually, thinking about answering those questions. So thank you very much for that. And I think it's probably time to wrap here.
Thank you so much, Stephen. That was by far the most engaging session in terms of audience comments. I mean, as you've seen, there's like so many questions being asked. I would have one final question that was one of the audience questions that I was personally burning to hear your answer to, which is from Christian. Do we live in a simulation? And if we get closer to represent everything around us using computational methods, does it make the simulation hypothesis more convincing to you? That was a question that I'd love to hear your thoughts on.
Simulation is a philosophical muddle. It doesn't make any sense. See, the thing is, okay, it's a little bit complicated to unpack, but basically, what does it mean that, okay, so if the universe follows certain rules, you can say, well, the universe will sometimes make an exception. Sometimes there'll be a miracle that doesn't follow those rules. But probably we would imagine the universe follows definite rules. So then, in a sense, once it's launched, the universe is just going to do what it does. It's just exists and does what it does. So if you imagine the gamer who is running the universe, the question is, does the gamer actually do anything? Or does the gamer just press the start button and then the game runs? Then the question is, if you are kind of looking at the universe on the smaller scale, kind of, can you tell there was a gamer down there or not? Can you tell that there was some intentionality to the construction of the universe? Well, this gets into all of these questions about sort of the nature of intelligence and so on. But the real killer, as far as I'm concerned, is that what we've kind of realized is that our universe runs all possible rules. And that means that the gamer has nothing to do. Because in a sense, that what is happening is the universe this is this question about why the universe exists. The universe doesn't exist because there's some gamer out there who's simulating it and pressed the start button. The universe exists because it is necessary that the universe exists. Why is it necessary? Well, it's a question of, let's say we say 1 + 1 = 2. Okay, that is a thing which is necessarily true given the definition of one, the definition of plus, the definition of equals. It's not something where we say, well, if we take one stone, another stone, and we put them together, then we get two. It's not a thing of that kind. It's a necessary truth. It's a feature, an abstract feature of the nature of the terms we're using. And so the question is it the case that our universe is something which is a contingent truth, something where it just happens to exist because a gamer put in that cartridge and pressed the start button? Or is it that the universe exists because it necessarily exists? Because, and the point about this idea about Rooleads and all possible rules and all this kind of thing is, once you have the notion that the universe is just all possible formal rules necessarily exist. They are things that once they're just the consequence of definitions. They're not something where we have to ask, is there an actualization of these things? They necessarily exist. And so the question then is, how does that end up being our universe? And the thing we have to realize is, when we are embedded in that thing, we are embedded as part of that thing which necessarily exists. And the fact that we have a perception of the universe as something with concrete tables and chairs and all that kind of thing, that's something that you then have to have a theory of physics to see how that works. But it doesn't require the idea that there's any spark of deciding to make a universe. The universe necessarily has to exist. There's an important philosophical consequence of this, which is, if the universe necessarily exists, then so does mathematics. And they're actually the same thing. That this universe of all possible universes is also the universe of all possible mathematics is. And in a sense, mathematicians are like observers of that universe of all possible universes. They're just observers that sample that universe of all possible universes in a different way than we sample the physical universe. And that was a burst of rather complicated philosophy that it's probably said way too quickly. But I think the end result of that whole thing is that I think that the notion, the simulation hypothesis, is kind of a philosophically muddled idea, and this was probably too quick a description to really get through the point of that. It's a fun thing to think about. It's a good kind of conceptual thing to kind of wrap your brain around to understand why it doesn't make any sense. But I think in the end, it doesn't really make any sense. So I think it is a much more bizarre. The truth, I think, is much more bizarre than that. The truth of the sense in which we are living in this universe of all possible universes and sampling with the particular senses we have from what happens. That is, in a sense, a much more bizarre thing, and it's sometimes it's hard to remember. As we I kind of. Do you get these kind of visions of the whole universe kind of disintegrating and turning into just hypergraphs where space is knitted together by action of the hypergraph and all that kind of thing? Or do you actually, look at the actual, camera and screen that I'm looking at right now, and it seems like a real thing? But I think that's one of the things that's been an important intuitional thing, is this idea that the whole universe is ultimately computational. It's much less jarring today than it would have been at some times in the past, because it's like, well, we have computer screens and they're made of pixels, and that's a very, discrete, definite thing that we could sort of deconstruct and say, well, it's just made of pixels. But actually, we can plainly see that we get the perception of real things there. And that makes it a little bit less shocking that our whole universe, when we kind of drill all the way down, is just made of stuff that's like some sort of very low-level version of something like pixels. All right. With that, we probably need to finally wrap here. But well, that was fun for me, and so thanks very much. And
thank you so much, Stephen. This was wonderful. The audience truly loved it from watching the stream. So thank you so much for joining us virtually, and hopefully next year we'll make it happen in person in Transylvania.
That will be
thank
fun
you so
one
much.
Day. Yes, I look forward to it. Thanks a lot. Okay, bye for now.